let's talk about reduction and oxidation. So reduction oxidation is most frequently abbreviated redox. The reason being is that they always go together. You cannot have one without the other. So reduction oxidation involves the moving of electrons. So if you gain electrons, that's called reduction, and you're getting more negative. And if you lose electrons, that's called oxidation. You're getting more positive. So you're losing electrons. And there are two mnemonics to help you figure that out. So these are called half reactions. So you typically combine these and don't actually show the electrons. But reduction and oxidation is always paired together. So there are two mnemonics that I find helpful in remembering this. There's Leo says grr. So Leo the lion says grr. Lose electrons, oxidation. Gain electrons, reduction. So Leo says grr. Lose electrons, oxidation. Gain electrons, reduction. The other one I like is oil rig. Oxidation is loss. Reduction is gain. So, whatever helps you remember that. Oxidation is loss of electrons. Reduction is gain of electrons. But remember that the charges go opposite because electrons have a negative charge. So if I'm getting more electrons, I'm getting more negative. So in order to assess whether reduction and oxidation is occurring, we need to be able to assign oxidation numbers. So there are a set of rules that determine how you find your oxidation numbers. And you kind of just need to memorize these rules. There's not that many of them. But the way it works is that there's a series of rules, and the higher rules have priority over the lower rules. So rule 1 is that elements have an oxidation number of 0. So if I got iron, the oxidation number is 0. O2, that's an element, oxidation number 0. P4, oxidation number 0. So any element by itself, oxidation number of 0. Second is that monoatomic ions have an oxidation number equal to their charge. So sodium plus has an oxidation number of +1. Oxygen 2 minus has an oxidation number of -2. Chlorine minus has an oxidation number of -1, and so on and so forth. Then rules 3 to 7 refer to oxidation numbers for elements in compounds. Okay, so these ones are not necessarily in compounds, but the rules 3 to 7 are specifically for compounds. So in a compound, fluorine always has an oxidation number of -1, no exceptions. Oxygen always has an oxidation number of -2. Hydrogen has an oxidation number of +1. Halogens have an oxidation number of -1. And finally, the sum of the oxidation numbers of a molecule equals the charge on a molecule. So in carbon dioxide, the sum of all the oxidation numbers is equal to 0. In carbonate, 2-, the sum of all the oxidation numbers is -2. And you'll notice that not most elements are not on here. The oxidation number of an element that's not on here you find deductively using math. So let's look at some examples. Methane. Okay. So the way we do this is we say, okay, hydrogen has an oxidation number of +1 from the rules, right? And I have 4 of them, so that's a total of +4. And then because the charge on the molecule is 0, carbon has to have an oxidation number such that the oxidation number of carbon +4 equals 0. Right? So my oxidation number of carbon +4 times 1 is equal to 0. So x plus 4 equals 0, so x is equal to -4. Carbon monoxide, right? Well, oxygen always has an oxidation number of -2 in a compound. So, in this case, x plus 1 minus 2, 1 times -2 is equal to 0. So x minus 2 equals 0, so x equals +2. And it's similar to balancing the charges on ionic compounds, but it is not the same thing. These are not charges, they're oxidation numbers. So again, oxygen always has a -2 oxidation number in compounds. So in this case, I have 2 times -2, so x minus 4 equals 0, so x is +4. Okay, well, what about carbonate? Well, in carbonate, again, oxygen's still -2, but now I have to add up to -2. So x minus 6 equals -2, so it's still just +4. Okay. So that's the general gist of how you're going to find oxidation numbers. Now, you can do this for bigger compounds. But let's look at some of those exceptions. Okay, oxygen difluoride. Well, we know that fluorine is always -1, but we also know that oxygen is always -2. But if we look back at our rules, the fluorine rule, that fluorine is always -1, is higher than the oxygen one, so the fluorine one takes precedence. So fluorine being -1 overrules oxygen being -2. So because the oxidation numbers have to add up to 0, x -2 equals 0. So in this case, oxygen is +2. And that's, I think, the only exception for oxygen. Let's look at O oxygen dichloride. So again, the halogens are usually -1. But the oxygen rule is higher than the chlorine rule, the halogen rule. So oxygen gets -2 and chlorine gets +1. Okay, so in this case, you have two of them. So 2x, right? So 2x minus 2 equals 0. So 2x equals 2. So x equals, right? Right, plus 1. What about SF6? Well, again, fluorine is always -1, and there's 6 of them. So sulfur ends up being +6. Sodium phosphate. Well, so this is an ionic compound. So we got to think about sodium being +1. Okay? So we know sodium's +1, and we know oxygen's -2. So 3 plus x plus 4 times -2 is 0. 3 plus x -8. So x minus 5 equals 0. So phosphorus equals +5. And that's, so you're doing math. Okay? Very similar to like finding the charge on a transition metal. So let's do some practice. First, find the oxidation number of chlorine in perchloric acid. So we know that oxygen is -2. We know the hydrogen is +1. Those rules are both more important than chlorine, so chlorine is going to have to deal. So I've got a total of -8 from oxygen and +1 from chlorine, and it needs to equal 0 because there's no charge on the molecule. So x -7 equals 0. X equals +7. Find the oxidation number of sulfur in SO2 minus, or sorry, SO2, just SO2. All right, so again, oxygen is -2, so total of -4 equals 0, so x equals 4. Find the oxidation number of chromium in dichromate. So here I've got -2 from oxygen, so -16 from the oxygen, and it has to equal -2. And I've got 2 chromates, so 2x. So 2x equals 14. X equals 7.